Hello and welcome. My name is Maciej Soja, and in this video I will talk about spaceborne measurements of forests. Airborne systems are useful for occasional acquisitions at regional scales due to their relative ease of access and low deployment costs. However, for large-scale monitoring they become too inefficient. Instead, satellites are used. Unfortunately, the deployment costs of satellites are high and their lifetime is relatively low, rarely longer than 10 years. Land-observing satellites are usually positioned in a low Earth orbit, at altitudes between 500 and 800 kilometers. This typically gives a trade-off between the air drag, resolution, and coverage. Often, satellites are located in polar and sun-synchronous orbits, which gives global coverage and even illumination of the solar panels and of the ground surface. Optical satellites in the low Earth orbit can acquire still images in the nadir direction at resolutions of the order of a few decimeters. In other words, it is impossible to read vehicle registration plates from spy satellites, both due to too low resolution and a steep look angle. Also, since satellites in the low Earth orbit move with a speed of approximately 7 km per second, video surveillance is not feasible. The use of geostationary satellites at 36,000 km altitude would allow video surveillance, but at the cost of resolution, which would drop to a few hundred meters. Many optical satellites make acquisitions at several frequency bands, not only in the visible part of the spectrum, but also in the infrared region. Spaceborne optical imagery can be found on, for example, Google Earth, which in recent years has become a very popular tool for scientists as well as for families planning their holiday trips. As a primary image source, Google Earth uses data acquired with Landsat satellites. High-resolution imagery acquired with airborne systems is also used wherever available. The Landsat program is the longest-running Earth observation program. The first satellite was launched in 1972, and currently 2 satellites are active. Landsat 7 launched in 1999 and Landsat 8 launched in 2013. The program has provided nearly 40 years of spaceborne imagery of the Earth. The latest Landsat satellite is able to acquire 11 spectral bands at resolutions from 15 to 100 meters. Time series of Landsat data can be used to detect forest cover change. On globalforestwatch.org, an interactive map showing tree cover loss and gain over the last 15 years can be found. For example, we can clearly see the damage caused by a forest fire that occurred in Sweden in 2014. In November 2015, European Space Agency ESA selected FLEX to become the 8th Earth Explorer mission. FLEX will be a satellite devoted to measurements of fluorescence on a global scale. It will consist of 2 spectrometers measuring reflectivity between 500 nanometers and 780 nanometers. The spatial resolution of FLEX will be 300 meters times 300 meters. Its launch is planned for 2022. As the resolution and coverage of laser scanners decrease with range, spaceborne laser scanners suffer from low resolution and coverage. Moreover, they are susceptible to cloud coverage. However, laser scanners have good vertical resolution and they can still provide us with a lot of interesting information on forests. One example of a spaceborne laser scanner is the Geoscience Laser Altimeter System, or GLASS, which was mounted on the American satellite ICESat and designed for measurements of ice, clouds, and land topography. This map shows the point density achieved with GLASS over forests, after removal of pulses with too low quality. Even in the regions with the highest pulse density, only a few pulses per square kilometer can be used for forest parameter estimation. Nevertheless, GLASS data can still provide useful information on forest structure. This map shows global forest height estimated using GLASS data in combination with data from other satellite sensors. A new spaceborne mission using laser scanner is planned by NASA. Global Ecosystem Dynamics Investigation, or shortly Jedi, will be a laser scanner mounted on the International Space Station. Its main goal will be to map forest biomass at an approximate resolution of 500 meters times 500 meters. However, the coverage of Jedi will be limited in latitude to roughly 50 degrees due to the orbit of the International Space Station. It will therefore not cover the boreal zone. The launch of the Jedi mission is planned for 2018, and the mission is scheduled to run for at least 1 year. Both optical and laser systems are typically restricted by cloud coverage. If we look at the distribution of clouds over the entire globe, we can observe that some land regions can be cloud covered 60 to 70% of the time a satellite passes. Especially in the tropics, the use of optical sensors is difficult due to the cloud coverage. As mentioned earlier, radars are cloud penetrating. Moreover, they provide their own illumination, and high resolutions are possible due to coherent signal processing. The first civilian spaceborne SAR system, CSAT-1, was launched by the US in 1978. Later, in the 90s, the European Space Agency, Russia, Japan, and Canada launched their own SAR satellites. Germany and Italy joined during the first decade of the 21st century, and South Korea, China, and India followed shortly thereafter. Within the coming years, Argentina, Spain, and the United Kingdom will also launch their own SAR systems. Currently, the number of active SAR satellites is around 20, and this number is steadily increasing. European Space Agency, ESA, has a long-running series of C-band SAR satellites designed primarily for maritime surveillance. The first satellite in the series were the near-identical ERS-1 and ERS-2, launched in 1991 and 1995. The ERS satellites were followed by Envisat, an enormous multi-sensor satellite launched in 2002. Currently, the newest satellite in the family is Sentinel-1A, launched in 2014, which is the first SAR satellite in the Copernicus program, ESA's global monitoring program. As we mentioned in the previous video, C-band is far from optimal for forest imaging due to the strong scattering in the top of the canopy. However, a dataset of 70,000 C-band SAR images acquired with ESA's satellites have been used to create this map of growing stock volume, which is correlated with biomass. Note the clear longitudinal trend in Siberia, while biomass decreases with increasing latitude. Also, see the high biomass levels in the temperate rainforests along the Pacific coast of North America and the low biomass levels in the grass-covered steppes and tundra. As mentioned in the previous video, lower radar frequencies are better for forest imaging. In May 2013, ESA selected biomass to become the 7th Earth Explorer. Biomass will operate at P-band with a wavelength of approximately 70 centimeters, and it will be the lowest frequency SAR in space thus far. Biomass is designed to produce biomass and forest height maps with a grid of 200 meters times 200 meters. Its launch is planned for 2020. Biomass will use many different SAR acquisition modes. The transmitted and received polarizations will be controlled, allowing the scientists to study scattering mechanisms at P-band. Moreover, due to the high temporal stability of scatterers at P-band, multiple acquisitions at slightly different incidence angles can be used together to obtain information about the vertical structure of the forest. Currently, a lot of research is focused on the development of algorithms for forest parameter estimation from biomass data. Spaceborne imaging systems provide us with an unprecedented coverage and acquisition frequency. Optical satellites provide us with images that are easy to interpret and contain a lot of useful information, but they are susceptible to clouds. Laser satellites provide us with accurate measurements of height and the vertical structure, but at the cost of poor resolution and coverage. And they are also susceptible to cloud coverage. Satellites with synthetic aperture radar, or SAR, provide us with cloud-free images with high resolution, good coverage, and good flexibility. However, the interpretation of SAR data is difficult. After all, our eyes are not used to seeing the world at such long wavelengths. Thank you very much, and goodbye.